In July 2025, the Atlas survey in Chile caught something impossible, a faint streak in the night sky, moving too fast, too strangely to belong to our solar system. Not orbiting the sun, just slicing through, a visitor from the interstellar void. They named it 3I/ATLAS, the third confirmed interstellar object in human history. Oumuamua in 2017 was a shock, a cigar-shaped enigma that sparked debates about its nature. Borisov in 2019 played by the rules, a comet with a familiar chemical glow. But Atlas, this third intruder, is rewriting the story entirely. Within days of its discovery, telescopes worldwide locked onto its path. The data poured in, and what astronomers saw stopped them cold. Atlas wasn't traveling alone. It was splitting apart, fragmenting into multiple pieces, each glowing faintly in the darkness. And here's the part that sent chills through observatories. Those fragments aren't drifting aimlessly. They're moving together, holding a pattern, a formation that defies everything we thought we knew about comets. The internet erupted, forums buzzed with theories, natural breakup, cosmic coincidence, or something deliberate. Scientists scrambled to explain it, but the question burned. Are we watching a random event or something orchestrated by physics we don't yet understand? Let's rewind to the moment of discovery. July 1st, 2025, the Atlas telescopes, four robotic sentinels scanning the sky for threats, picked up a faint anomaly. Machine learning algorithms, trained to spot the unusual, flagged it instantly. A hyperbolic trajectory, meaning it wasn't bound to our sun's gravity. This wasn't a local comet or asteroid. It was an outsider, born around another star, crossing through our solar system on a one-way trip. Initial velocity readings clocked it at 28 kilometers per second, fast but not blistering for an interstellar object. Oumuamua screamed through at over 80 kilometers per second. Borisov hit 40. Atlas was calmer, steadier, almost deliberate in its pace. Orbital analysts traced its path backward, running simulations that stretched years, then centuries, then millennia. The numbers suggested something extraordinary. A TLAS wasn't a lone wanderer. Its trajectory hinted at a stream, a dynamically cold flow of objects moving together through interstellar space. Imagine a river of ice and rock, ejected from a distant star system, flowing through our galactic neighborhood. Atlas was just the first piece we caught, the tip of a cosmic current carrying fragments from another world. Within 48 hours, the global astronomy community mobilized. The James Webb Space Telescope pivoted to capture infrared spectra. Hubble refocused to track its motion. Gemini North and South, perched on opposite hemispheres, worked in tandem to map its position. The first images were grainy, but they showed something no one expected. Multiple bright spots surrounding the main nucleus. Not part of the comet's tail, not background stars, but distinct objects, each trailing its own faint glow. Social media lit up with speculation. Amateur astronomers enhanced the images, circling the anomalies, zooming in on pixelated dots that seemed to move in sync with ATLAS. The question spread like wildfire. Is this a breakup or a coordinated group? Scientists cautioned restraint, but the data kept coming, and it only deepened the mystery. The fragments weren't scattering as they should. When comets break apart, pieces drift chaotically, pulled apart by gravity or their own outgassing jets. These objects were holding a pattern, a loose but undeniable formation, like birds flying in a V or satellites orbiting in sequence. The term formation pattern started appearing in research papers, cautious but unavoidable. It wasn't just a poetic description, it was a measurable phenomenon, and it demanded an explanation. Let's break down what we're seeing. When a comet approaches the sun, solar heating vaporizes its ices, creating jets of gas and dust. These jets can tear a comet apart, ejecting chunks that drift alongside the main body for days or weeks before dispersing. That's the first possibility. A TLAS is fragmenting naturally, its pieces temporarily holding together due to shared momentum. The second possibility is optical illusion. Telescopes tracking a fast-moving object like ATLAS smear background stars into streaks, creating the appearance of nearby objects. NASA flagged this in their Hubble analysis, noting that some bright spots could be stars blurred by the telescope's motion. But here's where it gets tricky. Not all the spots match this explanation. Some are persistent, moving with ATLAS across multiple images, defying the star smear hypothesis. The third possibility is the one that keeps astronomers up at night. The fragments are real, and their formation isn't random. They're influenced by something, physics we understand or forces we don't. Early data from JWST offered a clue. Atlas is venting massive amounts of carbon dioxide, 85% of its vapor mass, a ratio unseen in any comet, interstellar or local. This CO2 dominance suggests a birthplace far from any star's warmth, a frigid zone where only the most volatile ices can form. Could these jets, erupting with synchronized intensity, be pushing the fragments into a pattern? Or is something else at play, something that makes ATLAS behave like no other object we've studied? The chemistry alone is a bombshell. Most comets, even interstellar ones like Borisov, are water-rich, with H2O ice dominating their cores. Atlas flips the script. Its CO2-heavy composition points to a formation environment colder than anything in our solar system, perhaps an outer disk around a red dwarf star, where temperatures hover near minus 120 degrees Celsius. Water freezes closer to a star. CO2 needs the deep freeze of a stellar hinterland. This makes Atlas a chemical time capsule, a relic from a planetary system governed by alien rules. But the fragments add another layer. If they're real, each piece carries the same exotic chemistry, CO2, ice-laced with trace hydrocarbons, possibly even complex organic molecules. Imagine multiple samples from a distant world, not just one comet, but a cluster, each fragment a snapshot of a star system light-years away. The James Webb Space Telescope's infrared spectra confirmed the fragment's composition matches the main nucleus, ruling out random debris. These aren't stray rocks or unrelated objects. They're parts of ATLAS, broken yet bound together, moving as a group. This raises a question. How does a comet, stable enough to survive millions of years in interstellar space, suddenly split into pieces that don't scatter but travel in formation? The motion is where things get truly bizarre. Orbital mechanics are unforgiving. Gravity dictates paths with mathematical precision. The sun pulls, planets nudge, and objects obey. Atlas and its fragments don't quite follow the rules. Their trajectories show subtle deviations, tiny shifts that shouldn't exist. Each fragment moves slightly off its predicted path, but in a way that keeps the group cohesive. Scientists first pointed to outgassing. CO2 jets, erupting from each fragment, could act like thrusters, nudging them into new trajectories. JWST's real-time monitoring shows these jets are active, spewing gas at rates that could explain small course corrections. But the precision of the formation is what's baffling. The fragments aren't just drifting together. They're adjusting their paths in ways that suggest coordination. If each piece is venting CO2, the jets should push them chaotically, not align them into a pattern. One hypothesis gaining traction is mutual gravitational influence. If the fragments are massive enough, say kilometer-sized chunks, their gravity could tug on each other, stabilizing the group into a loose formation. Another idea, more speculative, involves magnetic fields. If Atlas contains metallic grains, aligned by a distant star's magnetic field during its formation, those grains could interact with the solar wind, subtly steering the fragments. Both theories stretch our understanding, but they're grounded in physics we can test. Now let's address the wild speculation. The internet is ablaze with claims of a fleet or alien convoy. The formation pattern fuels these theories, but science offers clearer answers. The bright spots are likely a mix of real fragments and optical artifacts. The real fragments, venting CO2, move together because they share the same origin, the same composition, the same response to sunlight. Their formation isn't artificial, it's a natural consequence of their breakup dynamics, possibly amplified by mutual gravity or solar wind interactions. No evidence suggests anything beyond physics at work. Yet the pattern is real, measurable, and unlike anything we've seen. To understand it, astronomers need more time, more data, more observations before Atlas, and its fragments race too far to study. The clock is ticking. By mid-2026, Atlas will swing past Jupiter, and that encounter will change everything. Jupiter's massive gravity will act like a cosmic lens, bending the paths of ATLAS and its fragments. If they're loosely bound, Jupiter could scatter them, pulling the formation apart. If they hold together, it'll confirm something extraordinary: a group of interstellar objects moving as a unit, defying the chaos of gravitational tides. This encounter will test our models, refine our predictions, and tell us whether ATLAS's formation is a fluke or a glimpse of a new cosmic phenomenon. The stakes are higher than just one comet. Atlas's discovery proves we're entering a new era. The Vera Rubin Observatory, set to go fully operational in 2026, will scan the entire sky every few nights, catching transients and movers with unprecedented speed. Estimates suggest it could detect dozens of interstellar objects yearly, each a potential ATLAS with its own mysteries. Before Oumuamua, we thought these visitors were rare, once-in-a-century events. Now we know they're common, part of a galactic flow that's been crossing our solar system for billions of years. Each one carries clues about distant stars, their planets, their chemistry. Atlas's fragments, if they hold their pattern, suggest that some interstellar objects travel in groups, bound by forces we're only beginning to grasp. This could rewrite how we model the interstellar medium, the vast space between stars where comets like Atlas drift. Are there streams of objects, like cosmic highways, channeling debris from one star system to another? If so, Atlas is our first map, its fragments the first markers of a route we didn't know existed. Let's zoom out to the bigger picture. Interstellar objects like Atlas aren't just scientific curiosities. They're messengers from the galaxy's past. When stars form, they create disks of gas and dust, the raw material for planets and comets. Most of that material stays local, but some gets ejected, flung out by gravitational chaos or stellar winds. These ejected pieces become interstellar wanderers, carrying the chemical fingerprints of their birthplaces. Atlas's CO2 dominance tells us it formed in a cold, distant zone far from its parent star's heat. Its fragments, moving together, suggest that entire clusters of objects can be ejected as a unit, traveling millions of years without scattering. This challenges our models of planetary formation. In our solar system, comets form in the Kuiper Belt or Oort cloud, regions we thought were typical. Atlas hints at stranger nurseries, places where CO2 ice dominates, where objects form in tight groups that stay cohesive across light years. If these streams are common, every star system is part of a galactic exchange, swapping material with its neighbors. Earth's water, its organic molecules, even the seeds of life itself might have come from objects like Atlas, delivered billions of years ago by interstellar comets crashing into a young planet. The Jupiter encounter in 2026 will be a crucible. If the fragments scatter, we'll learn how interstellar objects behave under intense gravitational stress. If they hold their formation, we'll have evidence of a new kind of cosmic structure, groups of objects moving together, bound by subtle forces. Either way, the data will shape future missions. NASA and ESA have concepts for rapid response probes, spacecraft designed to chase interstellar visitors. The Comet Interceptor mission, already funded, aims to launch in 2029, waiting in orbit for the next Atlas to appear. But Atlas itself shows why we need these missions now. We're watching it from afar, through telescopes, unable to touch its fragments or sample their ice. A probe could have flown through the formation, analyzed the CO2 jets, measured the fragments' masses, and confirmed whether their pattern is gravitational, magnetic, or something else. The technology exists. SpaceX's reusable rockets, JAXA's sample return expertise, Blue Origin's propulsion advancements. But the missions aren't ready. Atlas is a wake-up call. The next visitor could arrive tomorrow, and we need to be prepared to meet it, not just watch it slip away. The fragments raise another question. What else is out there? If Atlas travels with companions, how many other groups are crossing our solar system unnoticed? The Vera Rubin Observatory will answer that soon, but for now, ATLAS is our only window. Its CO2-rich fragments could carry organic molecules, the kind that spark chemical reactions on young planets. If these objects are common, life's building blocks might be scattered across the galaxy, delivered by comets moving in formation, seeding worlds with every pass. But there's a flip side. Interstellar objects can also bring risks. They move fast, unpredictably, and a large enough fragment could devastate a planet. Atlas poses no threat, but its successors might. Understanding their trajectories, their behavior in groups, is critical for planetary defense. Jupiter's gravity will give us a free experiment showing how these objects react to massive worlds. That data will help us predict future paths, assess risks, and plan deflections if needed. Atlas isn't just a curiosity, it's a test case for survival in a galaxy full of wanderers. Let's tackle the alien question head-on. The formation pattern sparks wild theories, but the science is clear. The fragments are parts of ATLAS, venting CO2, moving together due to shared origins and physical forces. No signals, no structures, no signs of artificiality. The pattern is extraordinary, but it's explainable through jets, gravity, or solar wind effects. The real wonder is natural. A comet from another star, splitting into pieces that hold together across light years, carrying alien chemistry to our doorstep. This isn't science fiction, it's science fact, and it's more profound than any conspiracy. Atlas's fragments are samples from a distant world, each one a puzzle piece from a star system we'll never visit. Their formation tells us the galaxy is alive with motion, with streams of material flowing between stars, connecting every planetary system in a cosmic web. We're not just observers, we're part of this exchange, receiving and sending material across the void. The story of Atlas builds on what came before. Oumuamua was a mystery, its odd shape and acceleration hinting at unknown physics. Borisov was familiar, a comet we could understand. Atlas is neither. Its fragments, its CO2 dominance, its formation pattern make it a new class of object, one that forces us to rethink the interstellar medium. Before 2017, we didn't know these visitors existed. Now 3 and 8 years, each wildly different, tell us the galaxy is diverse, unpredictable, full of objects we've only begun to catalog. The detection methods have evolved too. Oumuamua was a fluke, spotted by human eyes. Borisov was an amateur's catch. Atlas was found by algorithms, AI, sifting through data faster than any human could. The Vera Rubin Observatory will take this further, turning a trickle of discoveries into a flood. Soon we'll detect dozens, maybe hundreds, of interstellar objects yearly. Each one a chance to study another star's debris, to map the galaxy's currents, to learn what builds worlds and what threatens them. What makes Atlas unforgettable is its timing. We caught it early enough to watch it split, to see its fragments form a pattern, to measure their chemistry and motion. But we're still limited, stuck observing from millions of kilometers away. The dream is a probe, a spacecraft that can chase these objects, fly through their formations, and return samples to Earth. Agencies like NASA, ESA, and JAXA are working on it, but funding lags behind ambition. Atlas proves the urgency. Its fragments are drifting away, carrying secrets we can't reach. The next visitor might be even stranger, a nitrogen iceberg, a methane-rich comet, or another CO2 cluster moving in formation. We need to be ready, not just with telescopes, but with ships, ready to launch on a moment's notice. SpaceX's Starship, with its massive payload capacity, could carry interceptors. JAXA's Hayabusa missions show we can sample distant objects. The pieces are in place. We just need the will to act. Now let's look forward. Atlas's Jupiter encounter in 2026 will be a defining moment. If the fragments scatter, we'll learn how interstellar groups break apart. If they hold their pattern, we'll have evidence of a new kind of cosmic structure, one that could redefine how we see the galaxy. Either way, ATLAS is a turning point. It shows us that interstellar objects aren't just lone wanderers. Some travel in groups, bound by forces we're only beginning to understand. The CO2 chemistry tells us about alien worlds, places where ice forms in ways we can't replicate. The formation pattern hints at streams, rivers of debris flowing through the galaxy, carrying the raw materials of creation. Every star system is part of this flow, sending and receiving pieces of itself. Earth was shaped by this process, its oceans and organics delivered by comets like Atlas, billions of years ago. We're not separate from the galaxy. We're woven into its fabric, part of a system where matter moves freely, where worlds share their essence across light years. So what do you think? Are Atlas's fragments a fleeting coincidence? Or are we seeing the first evidence of cosmic convoys, groups of objects traveling together from distant stars? Is this a natural dance of physics, or a clue to something bigger, a galactic network we're only beginning to map? The answers are coming as telescopes keep tracking, as algorithms keep scanning, as the Vera Rubin Observatory prepares to open a new chapter. If you're captivated by the idea of a galaxy alive with wandering worlds, each carrying secrets from light years away, stay tuned. The next discovery could be days away, another piece of the cosmic puzzle, another message from the stars.